Here's the second shadow-related ray problem that I'd like to do with you. Um, this goes back to one evening when I was in high school. I had gone up to the corner store to buy some milk, and so here I am. This is aerial view, looking straight down, right? So here's me carrying my 2 gallons of milk, and I'm walking along, and I pass underneath a streetlight. So on the side of the road here, there's a telephone pole, and the streetlight is actually out over the street here, so it's, sending light out. And it was a winter evening. Did I mention that? It was winter. And it was snowing. And it was snowing one of those snows where the flakes are the size of golf balls and they're just falling very, very gently. It was absolutely gorgeous. The light reflects off the snow and just lights everything up. Even though it's nighttime, it feels like it's daytime. There's just so much light bouncing around. It was absolutely beautiful. And well, as I was passing under this streetlight, I got a very strange sensation. It was like the whole ground was rushing in at me. I had to stop and take a look at what was actually happening. And what was happening was that every snowflake, as it fell, was casting a shadow from the streetlight. So, the snowflake might have been falling over here, but the shadow was showing up over there. But as the snowflake fell, the shadow would move in towards where it was falling, and then as the snowflake hit the ground, the shadow, would hit the same spot right there. But this was happening from every direction, and it just felt like these shadows were zooming in really fast, and then they'd slow down and stop right where the snowflake landed. And this one be zooming in fast and then slower and then stop. And it was from every direction. It was just fascinating. And I didn't really know how to explain it at the time. I hadn't had calculus yet, but as soon as I got to calculus, I could do related rate problems. It's like, oh, now I can figure this out, because there was a question that I had as well as I was looking at this. As I'm looking at these shadows moving, and what's a shadow if it's not just a little patch of darkness? And they were moving really fast, and I got to wondering if maybe the speed of darkness is actually faster than the speed of light. Anyway, so here we go. Let's set up this situation. So this was the aerial view. Let's look at it from the side here now. So you've got your street light here, and the street light is probably got a 1,000-watt metal halide, or nah, it's probably more like a. Anyway, you don't care what the light bulb is. So I've got a snowflake falling, okay, and the light from the street light hits the snowflake, and then there's a shadow behind it because the light gets blocked by the snowflake, and so the light doesn't make it to the ground. So there's a little patch of darkness right there, which is the shadow of the snowflake. Okay, so let's see if we can set this up. Let's say that the snowflake is falling at maybe half a foot per second. Falls at a rate of half a foot per second, and it's not accelerating. At this point, the force of gravity that's pulling it down and the force of air resistance that's pushing it up are canceling each other out. So this is just coming down at a constant rate, just 1/2 a foot per second. Okay, let's give you some information here. Oh, well, that half a foot per second, that is a rate of change in some position. Well, it's essentially how the height is changing, right? So if I call the height of the snowflake that, what I'm told then is dh dt is equal to a half a foot per second. Actually, no, it's not, because this is falling. H is getting smaller, so this is minus a half a foot per second. Okay. I need to tell you how tall the street light is. Well, let's just assume it's the same street light as in the previous problem. So that was 20 feet high, right? So the street light's 20 feet tall. The height of the snowflake is changing, and the position of the shadow is changing. So as the snowflake falls this way, the shadow will be moving in that way, coming in, and they'll meet each other just as the snowflake hits the ground. Okay. I want to know how fast is the shadow moving? Well, to say how fast is it moving, I need a variable that's representing its position from some fixed spot. And I could go either from here or I could go from the street light. Let's just say, let's just call this length here x. And that's what I'm looking for right now, is what is dx dt. Right? The snowflake is falling a fixed distance away from the street light, and I'm going to have to tell you it's going to be different for each snowflake, but let's just pick a particular snowflake and say, oh, maybe this is, what do we say, 3 feet away from directly underneath. Okay. So dH dt is minus a half a foot per second. I'm looking for dx dt. How fast is that shadow moving? How fast is that length changing? Okay. Now, I'm going to do this as without knowing how high the snowflake is. I'm going to get this in terms of h because it seemed to me that this snowflake was traveling faster when h was higher up and slower when h was closer to the ground. And that's what I want to see if I can see how the speed changes as a function of the height. Right? So anyway, let's see if we can do this. The height, I have dh dt. I'm looking for dx dt. I need a relationship between h and x. Well, this is very similar to the last problem, and that we've got these similar triangles here. Let's say that x over h, so that's the little triangle here with the horizontal and the vertical side, is going to be equal to the horizontal side of the big triangle divided by the vertical side. So I agree with that. X over h equals x plus 3 over 20. Yes, I like that relationship. Similar triangles, ratios of corresponding sides. If you'd rather, we did the cotangent of that angle from the point of view of the small triangle and the big triangle. Okay, so they should be equal to each other. I can leave this relationship as it is. It is now perfectly good. However, I know what I'm going to do with it. I'm going to take a derivative with respect to t, and if I do that, I'm going to have to do a quotient rule. I'd rather multiply it out, maybe do a product rule. So I'm going to multiply both sides by the 20 and multiply both sides by the h. So I've got 20x equals h times x plus 3. Okay. I didn't have to do that, but because I know that I'm going to take a derivative, I'd rather do a product rule than a quotient rule, so I'm just choosing to write it this way. Okay. So now I have a relationship between x and h. I can implicitly differentiate to find the relationship between dx dt and dh dt. So here we go. Derivative of the left-hand side with respect to t is just 20 times dx dt. Right? The derivative with respect to x would have been 20. I didn't want the derivative with respect to x, I want it with respect to t, so then I just multiply by dx dt. That's the chain rule. Now, the derivative of this product. I've got h times the derivative of x plus 3. Well, that's just the derivative of x plus 0. So x dh dt plus x plus 3 times dh dt. So first times the derivative of the second, second times the derivative of the first, add them up. Now I have a relationship between dx dt and dh dt. I can plug in everything I know, solve for the one I don't. So what do I know? Do I know dH dt? I do. It's minus a half. Right? So I've got 20 dx dt equals h times dx dt. I guess I don't need that. Parentheses. Plus x plus 3 dH dt is the minus a half, right? Now, if I had a particular value of h I was interested in, then I could plug that in, and I'd also have to figure out what x is and plug that in. Because I don't know what h is, I still want to get this answer in terms of h, so I'm going to have to plug in for x. Right? So I'm going to take this thing right here and solve for x and then plug it back in for the x right there. I also have to solve for dx dt. But let's do this first. I'm going to solve this thing. Actually, I'm going to solve this thing for x. Right? So coming down here, I've got 20x plus h, plus, equals h times x plus h times 3. That looks too much like a function. So I just distributed the h in here. Then I'll get this x's over on the other side, so I've got 20x minus hx equals 3h. I can factor the x out now, so x times 20 minus h is 3h, and divide by that stuff, so x is 3h over 20 minus h. Now I can plug that in right there to get 20 dx dt. I'm going to bring this over to the other side. Minus h dx dt equals 3h over 20 minus h. That's the x that I just got. Plus 3 times negative a half. Now I can solve for dx dt. So I can factor that out and get a 20 minus h. Minus a half. I'm going to get a common denominator in here. So this is 3h, and then I've got a plus 3 times 20 minus h over 20 minus h. Okay. I'm going to divide by that 20 minus h, which is going to put another one down in the denominator here. So I've got dx dt is equal to minus a half times, this looks like a 60 on the top. I've got a plus 3h and a minus 3h, which cancel out. And so then I've got 20 minus h squared. And it's squared because I already had the 20 minus h there, and then I'm going to divide by this one and bring it over. Okay. For a grand total of dx dt equals, the 2 and the 60 will cancel out to just leave 30. I've got negative 30 over 20 minus h squared. Now, notice one thing here. 20 minus h, I'll draw the picture again. Here's the street light. The distance the street light to the ground is 20. The snowflake's over here. H was this much. So 20 minus h is the distance that it's fallen below the street light. Right? Notice that when h is 20, this thing is 0 and you're trying to divide by 0. The graph of this thing looks like this. Actually, I need to move this up. This is always negative. It's always negative. The negative, first of all, is because the shadow is approaching. Right? That shadow is moving in this way, so x is getting smaller. Hence the negative sign on the rate of change there, because x is getting smaller. But the graph of this is now h versus dx dt. There's a vertical asymptote at h equals 20. Which tells me that at some point, just as the snowflake falls beneath the height of 20, so you get just under the street light, that shadow is racing in at faster than the speed of light. So perhaps the speed of darkness is faster than the speed of light.